Now, when we try to understand the aromaticity of compounds, we cannot stop with applying the rules for aromaticity, but we need to understand, go a little further into the molecular orbital description of aromaticity and anti-aromaticity. As we know that the meaning of the word aromaticity has evolved as an understanding of the special property of benzene and other aromatic molecules, but originally aromaticity was associated with a specific chemical reactivity, because the first point where aromaticity came into picture was aromatic molecules were highly stable and they were unable to undergo chemical reaction. So the chemical reactivity of aromatic molecules differed, or it was totally different from those molecules which are non-aromatic in nature. The aromatic hydrocarbons undergo only substitution reaction in preference to addition. Later, the idea of special stability became more important. So this is actually a test to determine whether a molecule is aromatic or not, a simple test, a laboratory test. You can take some alkene, and if you try to add cold alkaline KMnO4 or aqueous KMnO4, the alkene would undergo hydroxylation and the KMnO4 will be decolorized. On the other hand, if you take an aromatic component, if you perform the same reaction, the reaction may not occur. Now, benzene was proved to show a lower in enthalpy than predicted by the summation of the normal bond energy for the C double bond C, C bond C and C bond H bonds in the Hückel representation of benzene, which we have already seen in our earlier lecture. The enthalpy of hydrogenation of benzene was much lesser when compared to the cyclooctatetraene, and this difference between the enthalpy of hydrogenation of cyclohexatriene and benzene corresponds to the resonance stabilization energy of the benzene. Therefore, aromaticity is now generally associated with this property of special stability which a molecule enjoys of certain completely conjugated cyclic system. Now, how does this stability comes inside a molecule? The major contribution of stability of aromatic system comes from the delocalization of pi electrons in these molecules, which also imparts other properties that are characteristic of aromaticity, especially a diamagnetic ring current. Please remember, this is again one important characteristic of an aromatic system. So if we take up an aromatic system, every aromatic system will have a delocalized pi electron, and this delocalized pi electron will induce a diamagnetic ring current inside the molecule, and this diamagnetic ring current can be tested or it can be detected with the help of NMR spectroscopy. So NMR spectroscopy is a tool to test the presence of aromaticity in a molecule. Now, aromaticity can be usually described in molecular orbital or Hückel molecular orbital technology, and we know that cyclic structures that have a particularly stable arrangement of occupied molecular orbitals are called aromatic. Now, whenever atomic orbitals combine together to form molecular orbital, we quickly go back and refer our Hückel molecular orbital theory. Now, Hückel's rule, a familiar expression of the relationship between a molecular orbital description of structure and aromaticity, is actually derived from Hückel molecular orbital theory and states that planar monocyclic completely conjugated hydrocarbons will be aromatic when the ring contains 4n plus 2 pi electrons, which is actually derived from your Hückel molecular orbital theory. Okay. Now, let us try to understand the descriptions for the molecular orbitals. Now, if we have a cyclic compound with 3 carbon system, so your Hückel molecular orbital calculation assign the pi orbital energies, and these pi orbital energies are obtained by solving the corresponding Schrodinger wave equation of that respective cyclic system or cyclic unsaturated system. So here the HMO or the Hückel molecular orbitals of the cyclic unsaturated system of the ring size 3 to 9 are shown here in figure. Now we have a dotted line here, and the orbitals below the dotted reference line in the figure are called bonding orbitals, and when they are filled, okay, say when they are filled, the molecule is stabilized. Okay, the orbitals that fall on the reference line, okay, so those orbitals that fall on the reference line, okay, those orbitals that fall on the reference line are non-bonding. Electrons in these orbitals are neither stabilizing nor destabilizing. Now this is the simple molecular orbital structure for cyclopropene. Okay, so this is the molecular orbital structure for cyclopropene, and this is your simple molecular orbital structure for cyclobutadiene. So you can have 2 electrons here, and the remaining electron can be placed here. So 1 electron here and 1 electron here. Okay. So the orbitals above the reference line are called anti-bonding orbitals, and any electron placed in this anti-bonding orbital, molecular orbital, leads to the destabilization of the molecule. Now this is the representation, molecular orbital representation for benzene. So in benzene we have 6 pi electrons. So we can draw the 6 pi electrons using Hückel's rule. Okay, and here the alpha corresponds to the Coulomb integral that we obtained from Schrödinger wave equation, and beta corresponds to the resonance integral, which are obtained by solving the corresponding Schrödinger wave equation, which actually contributes to the energy criteria of the molecular orbitals. Okay, so similarly we can have the molecular orbital description for 8 annulenes and 9 annulenes. All these values are obtained by solving the corresponding Schrödinger wave equation. Now benzene's extra stability can be explained by resonance alone, and so we must turn to molecular orbital theory for a fuller answer. How can we do that? Benzene has 6 planar sp2 carbon, and therefore each carbon atom has an unhybridized p orbitals, and these p orbitals are perfectly aligned for an overlap. Okay, so we can see something like this. So all these p orbitals, okay, so they are perfectly aligned for overlap. So they can undergo overlap. Okay. Now these p orbitals create a continuous ring of orbitals above and below the plane of the carbon atom. The 6 overlapping p orbitals create a cyclic system of molecular orbitals, that is a 3-dimensional system. Now even though we have only seen a 2-dimensional molecular orbital previously, namely our ethene and allyl system. So what I am meaning here is, say for example, if you try to draw the molecular orbital description for ethene. So this is how we will be drawing the molecular orbital description for ethene. So this is your molecular orbital description for ethene. So we have a bonding molecular orbital and an anti-bonding molecular. So let us say this is psi 1 and this is psi 2. So this is how you represent the 2-dimensional orbital for a alkene, that is ethene. Okay, so the same basic rules apply for even a cyclic system. So what we need to do is, the 6 p orbitals are used in the benzene pi system, therefore we have to create 6 molecular orbitals like how we have done in the previous diagram. And we also know that the lowest energy molecular orbital is entirely bonding. So constructive overlap happens between all adjacent p orbitals, and it will not have any nodes. So no nodes will be present in the molecular orbitals which are bonding in nature. So the number of node increases as the molecular orbital increases in energy. Okay, so the lowest energy molecular orbital does not have any node. As the energy of the molecular orbital increases, whether it is bonding or anti-bonding, the number of nodes also increases. So what is a node? A node is a place where the probability of finding an electron is 0. The molecular orbital must be divided between bonding and anti-bonding, with the possibility of non-bonding molecular orbital in some case, like how we saw it for cyclobutadiene. Now, so we are trying to understand the molecular orbital picture for benzene, and our current understanding on the structure of benzene is again based on molecular orbital theory. In benzene, all the 6 sp2 carbon atoms are arranged in such a way that each uses 2 of its hybridized orbital to bond to adjacent carbon atom, and the third one bonds to the 1s orbital of hydrogen. Now, the unhybridized p orbital associated with each carbon atom contain 1 electron and lie perpendicular to the plane of the ring. According to MO theory, these 6 p orbitals combine to form 6 molecular orbitals, 3 of which are bonding and 3 are anti-bonding. So please remember, it is only the unhybridized p orbital combined together. So we have 6 unhybridized p orbital, and these 6 unhybridized p orbital combined together to form 6 molecular orbital, out of which 3 are bonding and 3 are anti-bonding. So these are bonding molecular orbitals. Okay, so 3, and we have anti-bonding molecular orbital. Okay. So 6 pi electron. So according to the molecular orbital theory, these 6 p orbitals combine to form the 6 molecular orbital, 3 of which are bonding and 3 are anti-bonding. The 6 pi electrons occupy the bonding orbitals, which are lower in energy compared to the unhybridized p orbital. Okay. Now this is what exactly looks like. So you can see here we have the bonding molecular orbital. According to molecular orbital theory, you can see pi 1. So pi 1 is the lowest in energy, that is the lowest bonding molecular orbital, and you can see this, the 6 p orbitals. Okay, 6 pi bonding molecular orbitals, and the next is pi 2. Okay, so when the energy increases, you can see a node. So this is the node that runs. Okay, so it has one node, and here also you have one node. Okay, so you can see how these orbitals are actually placed. Okay, and for example, then we move on to the highest energy, which is anti-bonding molecular orbital, which is our pi 4 and pi 5, and here you can see there are 2 nodes. Okay, so we have 2 nodes here. So node is a place where there is a difference in the polarization. Okay, and in the other case you have 1, 2, 3. We have 3 nodes. So as the energy increases, the number of nodes also increases. So this is how we actually draw the pi molecular orbitals of benzene, and it is also represented in this way. Okay, so please, we need to practice this and we need to practice to draw the pi molecular orbital of benzene. The dramatic difference in the properties of cyclobutadiene, which is extremely unstable, and benzene, which is very stable, can be explained in terms of these Hückel molecular orbital diagrams. Now, in the case of cyclobutadiene, the electrons are arranged following the principles. Okay, so there are 4 pi electrons, out of which 2 pi electrons will be present in the bonding molecular orbital, 1 pi electron each will be present in the non-bonding molecular orbital, whereas in the case of benzene, all the 6 pi electrons will be present in all the 6 pi electrons will be present in bonding molecular orbital. So cyclobutadiene has 2 bonding electrons, but the other 2 electrons are unpaired because of the degeneracy of the 2 non-bonding orbitals. The 2 electrons in the non-bonding levels do not contribute to the stabilization of the molecule. The total Hückel molecular orbital energy is 4 alpha plus 4 beta. So each electron is alpha plus 2 beta. So alpha plus 2 beta, alpha plus 2 beta, and we have one more alpha and one more alpha. So the total is 4 alpha plus 4 beta, and this is same as for the 2 isolated double bonds. So if we have 2 isolated double bonds, okay, so this will be having 2 alpha plus 2 beta, and this will be having 2 alpha plus 2 beta, and therefore it is nowhere different between an isolated double bond and a cyclic system. Furthermore, as these electrons occupy a high energy orbital, they are particularly available for chemical reaction. Now, experimental evidence also indicate that cyclobutadiene is rectangular rather than the square. Now, on the other hand, higher level calculation agree with the Hückel concept in predicting cyclobutadiene to be extremely unstable molecule with a high lying higher occupied molecular orbital. Again, several methods of analysis also indicate that cyclobutadiene is not only highly reactive but is also less stable, which I have already seen than an isolated diene. So it is only for all these reasons that we say that cyclobutadiene is anti-aromatic, because it is not stable. It does not have any stability that can be correlated with aromaticity. On the other hand, simple Hückel calculation on benzene place all the electrons in bonding molecular orbital. So you can put all the electrons in bonding molecular orbital, okay, and the pi electron energy of the benzene molecule is calculated by summing the energies of the 6 electron. So we can sum up, so alpha plus 2 beta for 2 electrons in pi 1, alpha plus 2 beta, then this is 4 alpha, okay, plus 4 beta, because so each electron contributes 1 alpha plus beta, therefore 4 electrons, 4 alpha plus 4. So if you sum up, this becomes 6 alpha and this becomes 8 beta. So we have 6 alpha 8 beta lower by 2 beta than the value of 6 pi, sorry, this should be 6 alpha. So then the value of 6 alpha plus 6 beta for 3 isolated double bonds, okay. So beta contributes to the negative potential. Therefore, the corresponding calculation using Hückel molecular orbital shows that the energy criteria with respect to the electronic arrangement is equal to 6 alpha plus 8 beta, which is lower by 2 beta than the value of 6 alpha plus 6, because if you take 3 isolated double bonds, okay, each double bond contributes to 2 alpha plus 2 beta, okay, therefore 3 double bonds, it should be 6 alpha plus 6 beta, but our benzene shows 6 alpha plus 8 beta. So thus even the Hückel molecular orbital method predicts a special stabilization for benzene by a value of 2 beta.